Imagine a cosmic symphony played by an immeasurable number of stars, planets, and moons all playing in perfect harmony. However, there is one particular section of this orchestra that has perplexed astronomers for centuries: exoplanets. Exoplanets are natural planets that exist outside our solar system, hidden deep in the Milky Way. You might be surprised to learn that among the vast number of cosmic objects there are exoplanets so similar to Earth, so tantalizingly similar but enigmatic that they could be our planet's celestial twin. We delve into the fascinating realm of Proxima B, located just 4.2 light years away. The James Webb Space Telescope is revolutionizing our search for and understanding of these celestial enigmas. Imagine a moment when your mind travels across the vast astronomical realm of our galaxy, the Milky Way, which is home to more than a quadrillion exoplanets. That's one with 15 zeros to put this number in perspective. If each of these exoplanets were the size of a grain of sand, we would not only fill the Grand Canyon, but we would have enough to create a new geological monument on Earth, a Grand Canyon 2.0 that would stretch for miles. What is most surprising is that about 20% of these celestial bodies have been classified as Earth-like in terms of geological and atmospheric structure. That means there is a 1 in 5 chance of finding a twin of our planet, and the story doesn't end there. Along with these planets, there could be another quadrillion moons, rocky satellites similar to our moon, locked in gravitational dances with their parent planets. If you were to consider the possibility of discovering another body in space that harbors life or could do so, the cosmos offers an abundance of opportunities. Now that we have unfolded the canvas of cosmic scale, it's time to introduce the master artist equipped to paint its intricate details, the James Webb Space Telescope. This celestial Sherlock Holmes, with its magnified lens replaced by telescopic lenses, outperforms even the most advanced Marfan optics. We're not talking about just any lens. It's 6.5 mm in primary mirrors, 2.7 times larger than Hubble's. Imagine the finest detail it can detect, even in the faintest flicker of a star billions of light years away, and then analyze the details of orbiting planets. What makes the James Webb Space Telescope revolutionary is not only its observing power but also its advanced technology, including forward sensors and spectrographs. These tools can do much more than observe. They can analyze and filter the unique light signatures emitted or reflected by celestial objects to decipher their atmospheric conditions, composition, density, and even mass. Acting as space forensics, they can determine whether a planet has water, organic compounds, or even oxygen. The James Webb Space Telescope has the ability to answer these questions, elevating it from a mere observer to an analytical genius. It's not just an advance over its predecessor Hubble, it's more like a quantum leap. If Hubble's discoveries surprise you, get ready for a veritable feast of celestial revelations. Just as we broaden our gaze across the complex landscape of the cosmos, it's worth focusing on one particular star in the celestial show, Proxima B. Since its discovery in 2016, this enigmatic planet has stood out as a Shakespearean protagonist full of complexity and paradoxes, captivating astronomers and anthropologists alike. What's all the fuss about? For starters, Proxima B is practically in our cosmic neighborhood, just 4.2 light years from Earth. To put it in perspective, if you could beat the universal speed limit and travel at the speed of light, you would get there in just over 4 years, about the same amount of time it takes for your favorite TV show to fall into decay, or a presidential term. But let's dig deeper into why this proximity is so important. We're talking about a universe that stretches over 93 billion light years from end to end, so finding a planet so close and so promising for scientific research is like finding a Diamond in a pile the size of Mount Everest, a diamond that potentially holds secrets about life itself in the grand tapestry of the universe. Proxima B is an intricate stitch offering us invaluable clues that could redefine our understanding of habitability and life beyond Earth. It's not only Proxima B's proximity to Earth that excites the scientific community, but also the tantalizing clues that this planet is not only Earth-like but possibly Earth 2.0. Proxima fits comfortably in what astronomers call the habitable zone of its parent star, where conditions are neither too hot nor too cold but just right for liquid water to exist. Imagine waterfalls, meandering rivers, vast lakes, and perhaps even oceans as deep and mysterious as the Mariana Trench. But before we start dreaming about vacationing on Proxima B, let's consider some of the peculiarities. For starters, a single day on this intriguing exoplanet lasts a staggering 11 days. Imagine sunrises that not only herald a new day, but unfold slowly, resisting giving way to midday, and sunsets that stretch out, creating golden hours that photographers dream about. While it sounds idyllic, it also has significant implications for its climate and habitability. How would human biorhythms adapt to the cycles of light and dark on Proxima B? Would we need to eat 3 or 4 times as much in a single day on that planet? Would we sleep the same way on this very different world? The fundamental patterns of life as we know it would be at once tantalizingly similar and disconcertingly strange. It is as if nature is presenting us with a riddle, wrapped in a conundrum, testing our understanding of what makes a planet habitable. You may wonder how we can obtain accurate and reliable data about a world we have never visited. The James Webb Space Telescope deploys all its capabilities like a cosmic Swiss Army knife. More than just a telescope, it is a multifaceted research laboratory in the vacuum of space. Thanks to its innovative technology, astronomers not only observe planets but examine them through a prism of analytical tools that would make CSI labs look rudimentary. Using advanced spectrographs, the Webb telescope can analyze the light emitted and reflected by these remote planets. Each element or compound in a planet's atmosphere absorbs or emits light at a specific wavelength. By studying these patterns, scientists can perform a remote biopsy of celestial bodies, determining not only atmospheric pressure and density but also the possible existence of compounds essential to life, such as water, organic carbon molecules, and even oxygen. It's not just astronomy, it's space forensics. We don't wait passively for clues to come to us, we actively search for them, analyzing the atoms and molecules that make up these enigmatic worlds. The Webb telescope is not just an eye in the sky but a highly specialized laboratory analyst and cosmic detective all in one. It allows us to turn our speculations and hypotheses about alien worlds into methods to confirm or disprove them, revolutionizing our understanding of what might exist beyond our blue dot. Just when you thought you had unwrapped the most sensational layers of this cosmic onion, the story takes an unexpected twist. Just like in any science fiction thriller, researchers using the James Webb Space Telescope captured something extraordinary from Proxima B, a signal so unusual that it swept through the academic corridors and social networks. Labeled as a possible techno-signature, it was an electromagnetic emission so complex and enormously patterned that it could indicate the existence of an advanced civilization. The joint heartbeat of humanity seemed to stop at the climax of a revelation that promised to alter our perception of reality. Could the signal be the irrefutable proof that we are not alone in the universe? And just as quickly as it appeared, the signal disappeared without repeating itself, leaving behind not only an overwhelming silence but also a maze of unanswered questions and bubbling theories. Was it simply a transient cosmic phenomenon, a fluke of cosmic alignment or something more deliberate, a coded message, or even a manifestation of a haunting cosmic essence? The solitary mission cast the shadow of enigma over Proxima B, sparking intense debate and speculation. Was it just a passing anomaly, or is it part of a cosmic narrative far more complex than we can imagine? But wait, the narrative tapestry of our cosmic exploration is not complete. The ink has not yet dried, and new chapters are still being written. This time it is not just ordinary scientists but Harvard researchers who are leading a paradigm shift in our search for extraterrestrial life. They are not intent on just scrutinizing the signal and phenomena we have discussed so far. They are upping the game by transforming the James Webb Space Telescope into a sort of cosmic night vision telescope. Their goal is to search for artificial light sources in both the dark and illuminated areas of distant worlds. We're talking about staggering implications, such as the possibility of detecting terrace versions of cities glowing in the dark like luminescent SBS. Imagine seeing the radiant poles of what could be a metropolis humming with the presence of an advanced civilization, radiating its luminescence into the vast cosmic oceans. As we continue to unravel the mysteries of the universe, the quest for extraterrestrial life takes on new dimensions beyond the immediate intrigue of Proxima B. Our cosmic search delves deeper into the vast uncharted regions of space. This pursuit is driven by both technological advancements and a profound curiosity about our place in the cosmos. Recent developments in astronomy and space exploration have led to the discovery of numerous exoplanets with potential habitability instruments, like the James Webb Space Telescope. JWST and ground-based observatories have expanded our ability to detect and analyze these distant worlds. One particularly exciting field of study is the search for biosignatures, indicators of life. Biosignatures could include atmospheric gases like methane or carbon dioxide, which in the right conditions might suggest biological processes. The JWST capabilities extend beyond mere detection. Its advanced instruments can measure the atmospheric composition of exoplanets with unprecedented accuracy. By analyzing starite that filters through an exoplanet's atmosphere, scientists can identify chemical signatures indicative of life. For example, the presence of water vapor, along with other key molecules such as oxygen or ozone, might hint at the potential for life-supporting environments. Another avenue of exploration involves studying the climates of these distant worlds. Climate models based on data from JWST can help predict whether an exoplanet's conditions could support liquid water. This is crucial because water is considered a fundamental ingredient for life as we know it. Researchers are particularly interested in planets located in the habitable zone of their parent stars, where temperatures might allow for stable liquid water. The search also extends to the moons of exoplanets. Some of these moons, particularly those in the habitable zones of their host planets, could have environments conducive to life. For instance, icy moons in our own solar system, such as Europa and Enceladus, are thought to harbor subsurface oceans beneath their icy crust. Similar moons orbiting exoplanets might present analogous conditions where life could potentially exist. Furthermore, the concept of signatures has gained traction. These are signs of advanced civilizations that might be detectable through artificial structures or technologies. This could include megastructures like Dyson spheres, hypothetical constructs designed to capture a star's energy, or unusual patterns in radio signals. As we improve international collaborations in our observational techniques, the search for signatures could reveal the presence of extraterrestrial intelligence. In addition to technological advancements, international Collaborations are crucial in the search for extraterrestrial life partnerships between space agencies, research institutions, and private organizations enhance our ability to explore space. For example, missions to Mars and other celestial bodies involve contributions from numerous countries pooling resources and expertise to achieve common goals. Public engagement and education play vital roles in this quest. As well, the excitement surrounding space exploration inspires the next generation of scientists and engineers. Outreach programs and educational initiatives help foster an interest in STEM fields and encourage young people to pursue careers in space science. The development of new technologies also contributes to our understanding of the universe. Innovations in telescope design, data processing, and computational models prove our ability to detect and analyze distant exoplanets. For instance, next-generation space telescopes such as the planned Extremely Large Telescope ELT and the Habitable Exoplanet Observatory Habex promise to offer even more detailed observations and deeper insights into the potential habitability of exoplanets. As we push the boundaries of our knowledge, each discovery leads to new questions and areas for investigation. The search for extraterrestrial life is not just about finding alien civilizations, but also about understanding the origins and potential diversity of life in the universe. It challenges our perception and expands our understanding of what it means to be alive. In summary, the exploration of exoplanets and the search for extraterrestrial life are dynamic and evolving fields. With each advancement, we edge closer to answering some of the most profound questions humanity has ever asked. As we continue to explore the cosmos, the possibilities for discovering new forms of life and understanding our place in the universe remain boundless.